Greetings. I'm here in North Carolina, Asheville, and it's a nice spring day with some wind. A little breezy today. Class Y is on Feynman's derivation of the Schrödinger equation. And this derivation was the seed that led to his work in quantum electrodynamics that earned him a Nobel Prize, which he shared with Schrödinger and Tominaga. Now the story goes here back in the early 1940s when Feynman was working on his PhD, he went to a tavern, the Nassau Tavern in Princeton, and a gentleman sat by him, a professor, Professor Gell. He asked Feynman what he was doing. Feynman says, "I'm drinking beer." And he says, "Well, what are you working on?" And Feynman explained what he was working on and asked them if he knew any connection between the Lagrangian and quantum mechanics. Actually, Professor Gell did. He had read a paper by Dirac, a paper from 1933, in which analogy was made, a connection where the Lagrangian might be useful in quantum mechanics. The next day, they went to Princeton Library and found the paper, and when Feynman was reading it, he said, "What does he mean, analogous? This Lagrangian is analogous to something we're going to talk about in optics, a phase. And here, Feynman starts calculating, starts deriving things, and Professor Gell was very impressed what he's doing. He's seeing if he could derive the equation, the Schrödinger equation, using the concept of Lagrangian, phase, and a Green's function. It's very fascinating, and you're going to see a lot of the concepts in theoretical physics that we covered in our course. The Green's function and the Lagrangian integral tricks that we looked at earlier in the course, and the wizardry of Feynman to apply integral formulas when it's not obvious that the integral is really appropriate, or there's no, say, e to the minus alpha x squared, there's no minus sign in the exponent, there's an imaginary number, and Feynman proceeds and plows away anyway and derives the Schrödinger equation. So I hope you enjoyed this class on the Schrödinger equation and Feynman's wizardry in theoretical physics. Class Y, Feynman's derivation of the Schrödinger equation. First thing we're going to look at is the concept of path integrals and the path integral approach to quantum mechanics. This is the main idea of Feynman's PhD thesis at Princeton in the early 1940s. In other words, could there be a convolution for quantum mechanics? Because the idea here is that we're going to go from one point to another by looking at different possibilities, all the possibilities. So convolution for quantum mechanics. Now this will become clearer as we go. I'll be explaining more thoroughly when I write down the math, but let's start out with writing a convolution to get the state at a little bit later in time. So this is time epsilon, time interval. And here we're going to integrate from minus infinity to plus infinity over all the space. So here is the wave function at an earlier point in time, and we're going to integrate over all the space to sum over all paths to get from x prime to x. And that'll become more obvious what that means in the next section and the next section. All right, so let's look at Huygens principle, or the Huygens-Fresnel principle, and this will start to shed some light on this. Let's consider here a wave front in the past. you might think of this if I take water and hit it with a pencil like this, then a wave goes out, curvy at the edges, but a straight line, basically, a wavefront, a crest. If you replace each point with baby waves, and even closer than what I'm doing here, then what happens is that each baby wave, which is a circular wave, think of it like an impulse, then if you add them all up, the convolution idea, say here, then you're going to get the wavefront in the future. So this is the future wave front by obtaining all the baby waves and letting them evolve into the future. So since we're talking about waves, we talk about phasors. Remember e to the I kx. A phasor we use in electrical engineering, where you could take the cosine from that as the real part, and the imaginary part would be the sine, but it's easier to work with the exponential. So here, you can think of this as a lot of little wavelets or baby waves, and the baby waves have a form like this that you're going to then sum them all up. So let's review some wave parameters. K is 2 pi over lambda. We looked at that earlier in our course. And therefore, K times X is 2 pi over lambda times X. Note that the velocity of a wave is the wavelength times the frequency. So if you have 1 over the wavelength, well, if you had velocity over the wavelength, that'd be your frequency. And if you had 1 over the wavelength by itself, you'd have the frequency over the velocity. All right. So if I come over here and do that with the kx, I have here a 2 pi over the lambda times x, which is 2 pi, and this is going to be f over v times x. And now I'm going to bring in the concept of the index of refraction. Index of refraction is the speed of light in vacuum divided by the speed of light in the material. So for vacuum, n would be equal to c over c, and that's 1. So that's vacuum. If you look at air, it's so close, it's 1 again. And then if you look at water, you find 1.33, which I like to remember as 4/3. And then the glass would be 1.5, which I like to think of as 3/2. It's not exactly 3/2 or 4/3, but it helps me remember them. So if that is going to happen, then we're going to look at here a little modification. Let's put this f over speed of light in vacuum, and then c over v. And then this c over v is the index of refraction. And this is your 1 over lambda in vacuum, which I'll call like the reference, lambda sub naught. And if you multiply by 2 pi, you can consider it as some k reference sub naught. And then you would have the index of refraction times x. So if we are to look at the various, kx's that are up in here, like sum them up, you would say you could break down your path into little pieces where the index of refraction is changing, as you go, like this. And then you could imagine a continuous change. So if we then go to an integral, say k naught, some integral of nx dx, all right? So that means this idea of the phasor, so I'm going to say g here is proportional to this e to the I phase. The phase is going to be given by the k naught integral nx dx. All right. Now let's look at the problem that's very, very simple, saving a person that's drowning, to show you 2 different velocities and how this is going to work. Say you're in the sand, some lifeguard, and down here, help me, someone's in trouble. Now, the shortest path is not the best way to go because you run faster in the sand. So it's better to run a little bit more like this and then turn and swim the rest of the way. So this is the distance S1. We'll use S now in the 2 dimensions, S2. And here, time 1 is going to be, if you think of this as your distance, it's your velocity times time for the up in the top medium, medium 1, medium 2. Then this is going to be velocity 2 times T2. So this T1 is S1 over V1, and T2 is S2 over V2. And what I like about this example is that there is a principle of least time. So here, Fermat's principle of least time. You can consider historically the idea of least time dates back to Hero of Alexandria, and he basically saying that to go from point A to point B, light would travel in a straight line in the, say, a given medium, and this got generalized to more, say, complicated situations with the Fermat's principle where you have now index of refraction going on. And when this is imposed, you get Snell's law, for going from one medium to the other. So here, let's go back and write down what the N is. The N is a C over V. So that means 1 over V is going to be N over C. So if we do that, this is going to be N1, S1 over C, and this is N2, S2 over C. And when we generalize that, T is going to be some integral, 1 over C, integrate here the length ds, all right? And that's the principle of least time. So we have here 2 themes that are emerging, all right? 2 themes. Theme 1 is that we have the idea of phase and baby waves, all right? So that gets us the idea of e to the I phi, the baby waves. And then 2 is there's some minimum principle going on with an integral that's associated with it. So here, if you put the pieces together, you're seeing that this, phase is k times x, but then that got generalized to be this integral. So then we're looking at some integral up the exponent, all right? So that's one principle, and then the other is the minimum principle. Now in quantum mechanics, we're going to have the phase, and we're going to have a minimum principle of least action, all right? So let's go on here to Y3 and look at phase in quantum mechanics. So here we have the same idea, e to the I phi, and you may remember when we were talking about quantum mechanics, something like this can show up, all right, e to the I kx, all right? That's basically optics, because we already saw that here with the optics, all right? It's kx. So if you didn't have quantum mechanics, that's okay. We're just using this from optics, all right? And de Broglie will help us relate everything together. But before we do that, let's do a nice little problem, a very famous one, the two-slit problem, where you have, say, some electron source here, electrons shooting out like this, electrons. And here you get one path here, and there's another path down here, and they meet at a screen, say, like this. This is some screen. And the electrons, like light, they interfere. So here you have a wave. I go ahead and drop a perpendicular here like this. Then this is little d. This is big D, this distance here. And this is big D, all right? So 2 big D's and a little d. And the little d is going to mean that the lower one, this is the top one, is 1, 2. The second one is out of phase with the top one. It could be in phase or out of phase. It's going to be a different phase. If it's 2 pi, then we're back in phase again. And then you get like bright and dark regions up here when you have interference, or lots of electrons, no electrons, lots of electrons, this kind of thing. and in intermediate states in between the two extremes as they alternate. So if we look at this, we can then notice that the change of the phase, or the relative phase, is k times d. All right. Now remember, k is 2 pi over lambda, but de Broglie says electrons have a wavelength, h over p. Let's see. And then p is h over lambda. So if we look at this, we can replace 1 over lambda is p over h. All right. So that means this is 2 pi p, right, over h. And then we can say p is hk over 2 pi. And by definition, h over 2 pi is h bar. So just a review of some relationships here. This will come in handy in a second. So now let's see if we can consider a calculation of the action. Now the action is going to be equal to the integral of the Lagrangian with respect to time. All right, that's what needs to be minimized for each path. And here the Lagrangian is going to be kinetic energy, and that's it. There's no potential energy, so minus 0. Because the Lagrangian is going to be, your kinetic minus potential is what you basically have there, and there is no potential energy. So therefore, what we're going to do for the first one here, the straight line motion here, that we're going to see that S1 is going to be L1, which is a constant, because the velocity is constant, times t. So that's going to be 1/2 m, the mass, and the speed, this will be the d over the time t. That's squared multiplied by t. So what happens? You get m, d squared in the numerator, t squared in the denominator cancels with that t, so you get just 1t down there, so it's 1 power of t, and then the 2 survives over there. If we look at the lower path, L2, then we have 1/2 m, we have big D plus little d, all right, over t squared, and then there's a t here. So that's going to give us 1/2, or 1 over 2 t will survive just like here, but then the d is now replaced by d squared plus 2 big D little d plus d squared. Compared to these big D's, this little one's very, very small, so we're going to throw that away. And then when we subtract the two to find the change, all right, the delta in the action, S2 minus S1, you can see this first piece here, there's an M here I lost, put the M back. This first piece here is the same as this piece here, so that's going to subtract, and I'm going to wind up with the middle piece. So the middle piece, the 2's will cancel. I have M, big D, little d, over t. That's it. Now notice that big D over t is your velocity. So this is mv d. And this is your momentum. So this is p times d. All right. Now, with that p times d, we're going to, let's just go ahead and write that down over here, delta S, the change or in the action, the difference in the action is going to be P times D. All right. Now we're going to remember what we have up here. This says the change in the phase is K times D. All right. And then we're going to compare these, and what we're going to do with these two, we're going to say, well, the K and the D and the P and D, some relationship here, we're going to look at. All right, for the K, D, I go looking around, and I find this result, that P is H bar K. So if I look at that result, and get rid of that K, this is P over H bar times D. And here, by looking at the two of these together, I can see that the change in phase is the change in the action divided by h bar. So that's the conclusion. Very nice result. So now we're going to look at Dirac's analogy, because there's an analogy here we can make. And this is going to be Y4, Dirac's analogy. Now for Dirac's analogy, we're going to look at e to the I phi, which was what we had for optics and quantum mechanics. We had this for both cases. Now in the case for optics, the phase was written as some k naught, some integral, index of refraction, say ds. In quantum mechanics, here the phase is going to be 1 over h bar times the action, which is an integral of the Lagrangian with respect to time. Say. So with these two looking nice next to each other, this has a minimization principle. You minimize time. The principle of least time, Fermat's principle. And then over here, we're going to minimize the action. So a very nice analogy. And before we go on, I'd like to show you that this phase is dimensionless. So it's like radians. You can think of radians as like a ratio of two distances. So here, let's just look at this. Here, the dimensions of the k, dimensions of n, and dimensions of s. K is 1 over lambda, so this is 1 over meters. The index of refraction is a ratio of two velocities, so there's no dimensions there. And this is meters. So that means 1 over meters times meters cancels, and we have dimensionless quantity, which is what we want. So we have e to some dimensionless situation. Okay, let me show you that the action has dimensions of h bar, and then the h bars will cancel, all right, the dimensions. So the dimensions here of the Lagrangian and the time, say, t, this is going to get you, this is the dt, say, so this is going to get you energy. This is energy, and this is time, energy times time. So energy times time can be thought of as energy over frequency, since time and frequency have inverse relationship. And if you think of energy over frequency, you get h, since photon, hf is the energy. So that shows that the action has h bar units, or h units, and you're dividing by h bar, everything comes out very, very nicely. And it's neat to see the h as a parameter that's very, very important in quantum mechanics, see. So I think now we're ready for the derivation. So let's come up here and go here y5, the 5, and this is Feynman's derivation of the Schrödinger equation. I recommend you look at my textbook where I have pictures of Feynman and pictures of Dirac and Gel, and some quotes of how they were interacting in the Nassau Tavern in Princeton. Some neat stuff and some nice history there. All right. So here we're going to look at, to emphasize the two cases here where you have, say, x prime at some time t, and this is the x refer to the future, t plus epsilon, so this time frame is epsilon, and we fix a point in the future. We commit ourselves to being placed at a certain point, and we say that this wave function here is a result of looking at all these paths possible to get there from the past. So in other words, these paths all have the same time frame, even something way out here, see, coming from there. And the idea is that when you're looking at the phases are going to cancel when you sum up, and they're going to cancel for the bad pass, the wrong pass, and you're going to get the answer for the correct pass. That's the idea. It's as if all these paths were taken. Well, they weren't taken, but it's okay to think about it as taken. It's a very, very wild idea, the basic idea of Feynman's thesis at Princeton. All right, so that means we write down mathematically what we just said, that the wave function at x at some point in the future will be some integration over all possible paths. So here is your wave function in the past. We integrate over all possible paths, and this is the kernel or the propagator that propagates into the future. But all the paths are important. We're going to sum over everything. Wild. So this G, also the Green's function, right? X and x prime, right, is an exponential I t the action, and that action is given by the integral. So this is all the things we have looked at earlier in today's class. All right. Also the Green's function. All right. Okay. And now it's time to go to work it out. Work out all this stuff. Now, two references I'm going to be looking at. Derby's here. Derbys went ahead and looked at Feynman's original writings and pulled together things, filled in some steps, and made it clearer, more accessible. This is volume 6040 American Journal of Physics, 881, 884, 1996. And when I read this, I thought, this could be taught now to undergraduates, because I had encountered these ideas in quantum field theory in graduate school, taking courses in grad school. And when I saw this paper, I said, this is wonderful. This is going to be explained. That's what we're doing in this class. And then more recently, there's a paper here, Omri, I found online from the 2015 International Conference here of Math and Science Education. These are all given to you in my book that goes with this, the notes that go with this. So you can go ahead and look at that. I highly recommend you looking at those papers. They're very, very good. So here, let's put it all together. We have the wave function at some time into the future as given by this, the integral. We'll go ahead and write this out again. Write this out so we have it in front of us. This is some g of x prime, all right, x dx prime. Have it closer down as we work. And then we're looking at here to figure out what to do with the g. Now, this is interesting because when Feynman looked at that paper with Gell in the library, is it proportional or is it equal? All right. So in other words, do you take for the Green's function or the propagator the e to the I action over h bar, or is it proportional? Well, Feynman took the a to be 1, assuming it would be equal, and found that it wasn't, and then put the a in. So I'm going to put the a in first, no harm done. If they were equal, a would just turn out to be 1. Okay, we're looking at this integral where the Green's function here is going to be equal to or proportional to e to the I action over h bar. And we're looking at the action as an integral of the Lagrangian with respect to time from t to t plus epsilon, which we're going to approximate as an average Lagrangian times the time frame the delta time is going to be epsilon. So here we need to find the average Lagrangian, which would be the average kinetic energy minus the average potential energy. And for the average kinetic energy, we're going to take 1/2 m and the speed, delta x over delta t squared. Your delta x is going to be x minus x prime, that's squared, and the delta t is the epsilon. So you can think here, again, with this little picture, where if you have t here and t plus epsilon, and you fix a point here, and this is your x-axis, this is your x prime in the past, then different paths, say different paths are going to get you there. And as you look at your delta x is going to be your final x minus your initial x. And all these take place in the same time frame, epsilon, when you sum over all the paths, all the possible paths. So it's not likely something very, very far away is going to contribute much. So that takes care of the kinetic energy, and then the potential energy average, we'll just take that to be the midpoint. If you take x plus x prime over 2, that would be the average. And then for the action, we want to multiply by the epsilon. So the action here, like this, is going to be 1/2 m x minus x prime squared over epsilon squared times epsilon, and then minus v x plus x prime over 2 times epsilon. Now all of this has to be multiplied by I and divided by h bar to get you the exponent. And then you have to put it all up into the exponent. Wow, that's a lot of stuff. So let's write that out in detail. We will start it. Well, we'll start out by writing down this part, and then we'll have to do the integral. So the Green's function is equal to a times e to the I action over h bar, and that's going to be equal to a. Now here, I got all this in the exponent, so I have an exponent with some, u plus v. I'm going to write that as exponent u, and then exponential u times exponential v. All right, so I can just write them out like this, a little bit easier to see. So the exponential, for the first one, you have to have the I in there. So that I is going to come in here, Im, and then x minus x prime squared, and divide by, that's 2 h bar, and then an epsilon will cancel, and we'll have that. Then the second factor here is going to be the one involving the potential energy. So that's going to be minus v x plus x prime over 2. And now, what do we have here? We have an I is going to come in, I epsilon, and then we divide by h bar. So we're going to have that. That's what we're going to have for that. So here is where Feynman makes an introduction of a new variable, eta, which is x minus x prime, and it's kind of justified at this point by some clever thinking. Let me show you that. If I have x and t plus epsilon, now the wave function, if I come up here, I'm going to be using this thing, so I have to take this and do an integral. So I'm going to have here integration from minus infinity to plus infinity over all paths, a, now comes the g. I'm going to write this first one out, Im x minus x prime squared over 2 h bar epsilon. And then the second one here, what I'm going to do is I'm going to look at a Taylor series expansion since this is very, very small. If the epsilon is very, very small, then e to some small power is just going to be 1. And then, if you have e to some, say, u, that's going to be 1 plus u in higher terms. So if it's a minus u, then it's 1 minus u. So it'll be the minus sign, x plus x prime over 2 I epsilon over h bar. And then we'll have this thing, the function, wave function, and integrate over all possible paths. So that's a big thing there. Notice that the 1 over epsilon here, epsilon gets smaller, it gets big. And with Feynman reasoned that if this is very, very large, that's multiplying this x minus x prime, that quantity squared, then you're going to have lots of wiggles and squiggles. Like if you had something like sine to the 100 times x, that's a lot of squiggles, and the positive area will cancel a negative area. So he says the integration is only going to matter really when eta is almost 0, or 0, for example, 0 or the neighborhood of 0. So that was the justification of this parameter. I'm going to show you later that this is going to be something related to a delta function, where like delta, if you have a delta function, delta eta, that means that only when eta is 0, you get the contribution from the integral, and elsewhere it's going to be 0. But more of that later. For now, let's look at this translation of these variables, because that's going to be a little tricky. If you have the eta is x minus x prime, that takes care of this one. Over here, if you want x plus x prime, well, let's write down x prime here is equal to x minus eta. All right, and let's just write down a couple equations. And x is equal to eta plus x prime. So x prime here, if I bring on the other side of the equation, I have x minus eta. And if I am interested in getting rid of this x prime, because that x is considered a constant. See, that's constant. I'm integrating over x prime. So I want to get rid of x prime. So that means I will look at, say, this one, and say x plus x prime will be then 2x minus eta. And if I divide by 2, I get then x minus eta over 2. So that's what's going to go in here. The x prime one is easy. That's x minus eta. And now the dx prime, well, d eta is minus dx prime. See, x is constant up here, but I'm going to integrate over to x prime, and I got that negative. So that means when x prime went from negative infinity to plus infinity, the eta is going to do the reverse, from plus infinity to minus infinity. So these integration limits will be exchanged. And back over here, the dx prime will be equal to minus d eta. Now, if I put the integration limits back the way they are, then this minus sign will cancel. So that'd be a nice simplification. So let's write out all this stuff here, see what we got at this point. All right, we have the wave function in the future is going to be an integral from minus infinity to plus infinity, because I'm going to put the limits back and get rid of that minus sign. And this is a times e to the im eta squared over 2h bar epsilon. And then here I have 1 minus v. And what did we say for this combination is x minus eta over 2. And we have an I epsilon h bar hanging around. And then here, the x prime is x minus eta. And then this is a d eta. All right, so that's what we have to work with. All right. So when we get this far, it's time to do what Feynman did, and that is the zeroth order check. All right. And to do that, we're going to expand the function here, wave function, about eta, which is a small quantity. We're going to do a Taylor series expansion, which looks a little strange. I'm going to be showing you this bottom one in the class shortly, and I wanted to relate this one to one that we would see in calculus class. So here's a Taylor series expansion about z equals a, and a lot of times we have just the Maclaurin series where a is equal to 0. Then you would have here z and z squared. Notice you have here the evaluation of the function at a, or say a could be 0. And then here you would take the derivative and then put in a or 0, and etc. So to get this form that we're going to use down here, let the z be replaced by x minus eta, and let a be x. Then z minus a would be x minus eta minus x, which would be minus eta. And here you're going to square the minus eta. So you're going to get this down here. You could think of a dz is equal to a dx, and this is some shift on the z function, so therefore derivative with respect to z up here could be replaced by the derivative with respect to x down there. So this would be the wave function here at t. That would be the 0th order. And then what you would do is, like Taylor series expansion, the next one's going to be here minus the partial derivative with respect to x. So we're doing an expansion here. The first derivative, and you would put in a value for x, and this would then be the eta. And then you would have here the second derivative, and that would be eta squared. So this is first order in eta. This is second order, since the eta is squared. And this one here is 0th order, since you have eta to the 0th power. Now, what Feynman's saying here is that the check on this constant a to 0th order. So the 0th order check, what that's going to do is check that to 0th order, nothing's going to change. In other words, you're going to have this integral a e to the I m eta squared over 2h bar epsilon. This to 0th order, this epsilon is gone, and we just have a 1. And then we'll have this same thing here, and this is beautiful check, because what it's saying is that you're going to have to get the same result. It'll be more obvious what has to happen if I write out with pulling out this wave function and pull out the constant. Then this integral here, I am eta squared over 2 h bar epsilon d eta. When you integrate this, you have to get 1 over a, so that then the a's cancel. And this is where Feynman realized that he needed to have a proportionality constant, because when he did this, this wasn't there, and he knew that that would not get you 1. Well, what does that get you? Well, here's where Feynman does some wizardry. Now, we know that if we integrate from minus infinity to plus infinity, a v to the minus alpha x squared dx is the square root of pi over alpha. We've done that earlier in our course. Now here, there's no minus sign up in there. In fact, there's an I. What's going on? Well, Feynman plows ahead and does the integral using this formula anyway. That is wild, all right? So in other words, how do you get this to work? Well, if you say minus alpha is equal to I m over 2h bar epsilon, all right, then this will look like this. But look at this crazy stuff, All right, what's with this? So this is saying alpha is minus Im over 2 h bar epsilon. And if you'd like to get rid of that minus sign, it's not a problem. Multiply top and bottom by I, and you'll have m over 2 I h bar epsilon. Still weird. What's going on here? So looking at this answer here is going to be a square root of pi over alpha using this logic. And so therefore, if I have the square root of pi and I want 1 over the square root of alpha, I'm going to have a square root where I flip this because I want the 1 over alpha. So I want 2i h bar epsilon over m. All right, and if I bring the square root of pi inside, I would have 2 pi I. I kind of like that combination. It's easy to remember. So 2 pi goes in there, 2 pi I h bar epsilon over m. And we said that has to be 1 over a. So that means the proportionality constant, what goes out in front, has to be m over 2 pi I h bar epsilon. And these i's don't bother Feynman in the least bit. So that is really wild stuff. All right, so here we have then the wave function. We're going to go back and plug in here and write this out again. This is going to be, this a here is going to be the square root of m over 2 pi I h bar epsilon. And then we have the integral with this, minus infinity to plus infinity of e to the im eta squared over 2 h bar epsilon. And then we have this other stuff, 1 minus v x minus eta over 2, just copying down, I epsilon over h bar, and then copying down the wave function here, x minus eta t d eta. All right, now I want to focus now on this piece and this piece. Let's just look at this. This is interesting. E to the I m eta squared over 2 h bar epsilon, and then we have the square root in front, m 2 pi I h bar epsilon. Now remember way back in our course, we looked at the Gaussian. Here's x and some probability distribution where the area is 1. And we found the Gaussian in terms of standard deviation is given by 1 over the square root here of 2 pi alpha squared, all right? And then we have an exponential here with a minus x squared over 2 sigma squared. So that's sigma squared. Sigma is your standard deviation. So we looked at this and we said, let's go ahead and make the assignment a squared is 2 sigma squared. So this is the standard Gaussian you find in statistics. If we do that, then we get 1 over a times the square root of pi, since the 2 sigma squared is a squared. And then we get here e to the minus x squared over a squared. And then we said that this is a sequence of functions where if a gets smaller and smaller, then what happens is that this gets more peaked. It gets like a spike. And that's the delta function. So the delta function here was then the limit as a goes to 0 of the delta sequence. All right. Now let's look over here and let's consider what we have? Well, if we consider, say, make the assignment, say that 1 over a is equal to the square root of m 2I h bar epsilon, then this piece out in front is a 1 over a times the square root of pi. It's exactly what we have here. But then, if you look at what's up in here, it's going to be, if you square this, let's do that. Let's go ahead and see what we get if we do this. So let's take the 1 over a squared. Let's do that. And that's going to be m over 2 I h bar epsilon. And if we look at that, we can multiply top and bottom by minus I, all right, so that we get this. And then if we have minus 1 over a squared, then we get a plus im over 2h bar epsilon. That's exactly what we have here. So in other words, this is a minus 1 over a squared hitting the eta squared, just like we have here. And then out front is 1 over a times the square root of pi, the delta function sequence. Wow, so that means that the integral is going to be given, say, most of its contribution, or getting most of its contribution from when eta is near 0, or x is approximately x prime, which we said earlier, and Feynman had the argument with the oscillations, but now we can see what the delta function, I think, more clearly, and review the delta function for us to justify the whole idea of replacing x minus x prime with eta, and then doing expansions in eta, because what this is telling us is that you have something that's like this graph here that shows you have the contributions coming from near 0, your very immediate neighbors, and out here you get, it's flat, it's 0. So that's a very, very nice connection and a nice review of our delta function. So what needs to be done is to integrate this, work this out, and that's what we're going to do in the next step. All right, that's the last step, actually. So here we're going to look at, here we're going to write this over again because there's a lot of stuff here going on, and it's important to have it in front of us at all times. So we're looking at here an integral over all possible paths, e to the I m eta squared over 2 h bar epsilon. I'm just copying what we had done earlier. And this is going to be here the x minus eta over 2 and I epsilon over h bar. And then we have over on the far right x minus eta t d eta. All right. Now we're going to look at this, do an expansion on this thing. This is basically going to be evaluated at x, and here you're going to look at a minus and then your derivative here with respect to x, and then the eta over 2. So this is a Taylor series expansion on this part, neglecting higher orders, and then you'll have the I epsilon over h bar floating around. So if we make that assignment, and then we write out again to keep everything in front of us as we go. This is a minus infinity to plus infinity, e to the I m eta squared over 2h bar epsilon. Then we have 1 minus here. We're going to look at eta and epsilon is being super small, so we're going to just tossing that part. So that's nice. That's just going to be v of x I epsilon over h bar. And then now things are looking simpler. And this is the beauty of the theoretical physics, doing these Taylor series expansions like art. And then this a, if I write that down from the other page that we did, that's m over 2 pi I, that nice combination there, h bar epsilon. So now what Feynman does is another Taylor series expansion, which we looked at before. This x minus eta t, we have the 0th order term that we looked at earlier, then minus the first order term, right? And that's the eta. And then there is another order, the second order term, which is your second derivative here, eta squared. Now you might say, why are we doing that? I thought you threw away things that were eta squared and higher. Well, like we did throw away that there, but compared to this, but I'm not going to throw this away because when we do this integral, this one's going to be 0, and I'm going to need to have the next one. I'm going to have to go there, and that's going to get the second derivative, which is necessary for the Schrödinger equation. It's going to be really neat. So you have the three integrals, all right? We have integral 1, 2, 3, and let's label these. Here's the first integral is going to be with this one, and then the second one, and then the third one. So integral 1 is going to be, that's this one, that's constant. You can pull that out. And then we're going to have the a, and then the integral from minus infinity to plus infinity, e I m eta squared over 2 h bar epsilon. And then you got to put everything else in, 1 minus v of x I epsilon over h bar, and that's eta. So that one there is the first integral, and this is to first order in epsilon. This is your order, epsilon, okay? And then the second integral, that's this one here, and this is the constant. We can pull that out like this, all right, dx. And then we have a, and then we have the integral, same exponential, I m eta squared over 2 h bar epsilon. And then we have, with this, you got this one we're shoving in there. So this is going to have the eta in there, like that. And here, you say, what about this? Well, now, if I have an eta already there, I'm not going to want that extra epsilon, so I'm finished. This is good. This is going to be neglecting epsilon eta because that's doubly small, you know. So we're going to throw that away. However, this is an even function, and this is an odd function. This is odd. This is even. So this is going to be 0. And you might say, but I thought that's cosines and sines. Well, yes and no. If you look at this, e to the I u, then you would have cosine u and even, and you would have an odd. But suppose you have e to the I u squared, all right? Then you have cosine of u squared and I sine of u squared. Now you got an even function, because if you're going to have u squared plus or minus u, that doesn't matter. The sign of that's going to be the same. So this is why we had to keep an extra term in the third integral, because the second one gave us 0. So then the third integral is 1/2, and here is the second derivative, all right, a constant. We can pull all that out. This is dx squared. And then we have a times the integral from minus infinity to plus infinity, same exponential that we had before. And then here we have the eta squared. And there we don't worry about this again, because if we have eta squared, we don't want eta squared times epsilon. So we're basically finished with this one. So I'll just emphasize that we neglect the eta squared epsilon as three small things multiplied together, all right? So now it's time to finish the integrals. So let's look at that first integral. And it has this 1 minus Vx I epsilon over h bar. And here, this is all constant because there's no etas. And then here you have a is in there. And then we're going to go from minus infinity to plus infinity. E to the im eta squared over 2h bar epsilon d eta. So this is, we're coming up here. So let's check. We have, this is out in front. We have this combination out in front since there's no etas. And then we just have this integral, but we already did this. This is 1 because this is your normalization. A times that's 1. So we're finished. First integral is done. Second integral is done. 0. All right? So we're really moving along here. And the third integral has eta squared. The third integral is of the form minus infinity to plus infinity, v to the minus alpha eta squared d eta. And here's where Feynman was very fond of doing the derivative trick. This is minus the derivative with respect to alpha of the integral e to the minus alpha eta squared d eta, where here if you take the derivative with respect to alpha, you pull down at eta squared. And since we know this one is the square root of pi over alpha, then if we take the derivative, we're going to get here a minus, there'll be a square root of pi, and this will be a negative 1/2 will come down, and we'll have alpha to the negative 3/2. Since this is a square root of pi times alpha to the negative 1/2, to take the derivative, minus 1/2 comes down. And then you get alpha to the minus 3/2. Now this minus sign here will cancel the minus sign coming from the derivative. Say you pull that minus 1/2 down. So when you look at all this, you'll get a square root of pi, all right? And you'll have a 1/2. And I'm going to write this as a 1 over alpha and 1 over the square root of alpha. That's alpha to the 3/2, the negative 3/2 power, so that this becomes nice 1 over 2 alpha and then a square root of pi over alpha, like what I had before. All right, so now we have to remember what the alpha is. So the alpha here is equal to minus im over 2h bar epsilon, all right? And what is the A? Well, let's just write that down from before. A is equal to m over 2 pi I epsilon h bar, all right? So now we need to pull all this together. And for the third integral, let's write down for the third integral by putting all these pieces together. We have for the third integral, the 1/2 second derivative out in front. That's coming from this piece here. Then we have the A. And then after the A, we have the integral that we just did. And that integral that we just did is going to be here 1/2. And then we're going to, it's 1 over alpha. So we have to flip this alpha. This is going to be minus 2 h bar epsilon over im. And then we have to have the square root of pi over alpha. But remember, the A was the square root of alpha over pi, the normalization constant, so they cancel. And with them canceling, we are going to be left with, for I3, let's see what we have here. Okay, so let's see what we have. We have a 1/2 in the front here. We have this second derivative with respect to x. And then the these cancel, so we have left here, these 2's will cancel. We have minus h bar epsilon over im. All right. So we could multiply top and bottom by I, and that will get us then here a plus like this. And then we have the 2 goes with the m, and that's then the second derivative with respect to x. All right. Now let's write down here the integrals, the 2 integrals. We have x and then t plus epsilon. And the first integral that we did, all right, that's going to be this one here. It's going to have the wave function, x and t, and then we're going to have this factor here, which is the 1 minus v of x I epsilon over h bar. And then the second one is going to be, the third one, second one was 0, I h bar epsilon over 2m, second derivative with respect to x. All right, almost finished here, almost finished, almost got it here. So let's look at what we can do here to simplify a little bit. I like to write this out as 2 terms and subtract 1. So here is x t plus epsilon minus, right? So I subtracted this first one out, and I'm going to divide by epsilon, all right? And then what do I have over here? I have a minus the wave function times the v of x. And then I have I over h bar since I divided by an epsilon. And then this last one over here is going to be a plus I h bar divided by epsilon. Epsilon's gone over 2m. And here is the second derivative. All right. Now this here is freshman calculus. This is a derivative. This is the derivative with respect to time. So this is the partial with respect to time. I have the one at the final time minus the one at the initial time divided by delta t. See? So this is from calculus. And then I'm going to multiply by I h bar, start to look like the Schrödinger equation. And if I multiply by I h bar, then over here, I'm going to get the wave function times the potential, and then the I is going to be squared with the minus sign. It's going to go away, and I multiply by h bar, so I'm finished. That's what I got. And if I multiply by I h bar here, look at this. This is going to be a minus sign. H bar is going to be squared over 2m. Second derivative with respect to x. We got it. We are finished. We have I h bar, the partial with respect to t, is equal to minus h bar squared over 2m. And that's going to be the second derivative with respect to x, and then plus the potential energy times the wave function. This is the Schrödinger equation. Amazing. And look at that. The I shows up somehow from all this analysis, which is important in the Schrödinger equation. Look at this. H bar squared over 2m shows up. The minus sign. Everything shows up. This is amazing. Here's a photo of Dirac on the left and Feynman on the right. This is from 1962. When they first met back in the 1940s, the story goes that Feynman came up to Dirac to introduce himself, but he didn't know who Dirac was. You see, back in those days, they didn't have photos easily available. So I could imagine Feynman coming up to Dirac and saying, "Hello, I'm Dick Feynman." And then Dirac said, "I am Dirac," and there was silence. Someone had overheard this conversation and wrote it down. After a moment of silence, Feynman said, "It must be wonderful to be the discoverer of that equation." And Dirac replied, "That was a long time ago. What are you working on?" Well, Feynman asked Dirac at another time, when he met him, about the analogous term in the calculation that he worked on in terms of that Green's function. Was it proportional, or was it exactly equal to that exponential with the action? So then Feynman says, "Did you know that they were proportional?" asked Feynman. "Are they?" Dirac inquired. "Yes," said Feynman. "Oh, that's interesting," was Dirac's final comment. So yes, a lot of work here, but then that's often the case with theoretical physics to do the calculations. A lot of things. We've done a lot today, and you should be proud. You have seen a very advanced, understand a very advanced calculation that has great historical importance.